Hello my scholars, this is my school YouTube channel and I am Frank. In today's video we shall be discussing about structure of the nucleus. Okay, but for the purpose of convenience we are going to be sharing this topic into two parts. So today we are going to be considering the first part, while in subsequent video we'll consider the second part. So relax, do not go anywhere, I'll be right back. You are welcome back to my school YouTube channel. Like I said earlier on, we shall be looking at structure of the nucleus part 1. So as usual, before we begin with our lesson, let's quickly run through the objective for today's video lesson. So objective number 1, trace the historical development of atomic models from Thomson's model to the Electron Cloud model. 2, state and explain the major postulates, successes and limitations of Thomson's model, Rutherford's model, Bohr's model, Electron Cloud model. And 3, describe the structure and composition of the atom, identifying protons, neutrons, and electrons as subatomic particles. So let's begin with our lesson. So here under model of the atom, basically we are going to be looking at 4 models: Thomson's model, Rutherford's, Bohr, and the Electron Cloud model. Okay, and we are going to be looking at them under the following heading: postulates, successes, and limitations. Okay, so now let's begin with Thomson's model of the atom. Okay, so this model was proposed by an English physicist by name Sir J.J. Thomson. Okay, then under postulates, he said the atom is a uniform sphere of positive charge with negatively charged electrons embedded within it. He said he described it like plums in a pudding. Okay, so this is the diagram of the first postulate. Okay, so this is the sphere of the positive charge, and these are the negative electrons that are embedded inside the electron. Okay, so number 2, he said that the distribution of charges in the atom was diffusing. Okay, so let's move to the next slide. Now let's talk about the successes of the Thomson's model. Right, so 1, the model explains that atoms are not indivisible or indestructible, okay, but can disintegrate. Okay, so if you are a student of chemistry, then you understand this better. Okay, then number 2, the model explained that the atom contains enough positively charged components to balance the negatively charged ones, making the atom electrically neutral. Now remember that for an electrically neutral atom, the number of protons is equal to the number of electrons. So basically that's what the number 2 success is talking about. So now let's discuss about the limitations. Okay, so 1, the model could not explain why most alpha particles pass through a metal foil without deflection, suggesting that atoms are mostly empty space with a small, dense, positively charged nucleus. Then number 2, the model also could not explain the large deflection of a few alpha particles, which indicated the presence of a heavy nucleus at the atom's center. So these are the limitations of Thomson's model. Okay, let's move to the next slide. So on the next slide here, we are going to be discussing the Rutherford's model. Okay, so the Rutherford's model is also called the nuclear idea or the planetary model. So just take note of that. So the experiment for the scattering of alpha particle was performed by Ernest Rutherford and his co-workers in 1911. The failure of the Thomson model to explain the observations of the experiment made Rutherford to propose his model of the atoms. Okay, so now let's look at the postulate. So according to him, he said that the atom consists of a positively charged heavy core called the nucleus. Now remember that the proton is found in the nucleus and the protons are positively charged. Okay, probably that's why he said this. Where most of the mass of the atom is concentrated, and that around this nucleus negatively charged electrons circle in orbit in the same manner as the planets revolve around the sun. Of course, you know that the planet revolve around the sun, okay? Then number 2, according to him, he said that the nucleus must be surrounded by a number of electrons. I remember electrons are negative charges, sufficient to balance the positive charge of the nucleus so as to make the atom electrically neutral. So you can see that this second postulate also agrees with what Thomson said in his own case, okay? So for an electrically neutral atom, the number of protons, okay, is equal to the number of electrons, just to balance things up, okay? So let's move to the next slide. Now, this is just the diagram of the Rutherford model, okay? So now let's discuss about the successes. Okay, so let's see the successes of the Rutherford model. So this model was a major step forward on how we view the atom today. Okay, so one of them is that the model explains the scattering of an alpha particle through a large angle when an alpha particles are directed to a metal foil. Then 3, the model explains that the nucleus of the atom is very small but massive, and most of the atom is empty space, okay? Then 4 explains that the negatively charged electrons revolve around the positively charged nucleus, okay? So from here, we can actually bring out some conclusion from Rutherford's model, right? And one of the conclusions is that the nucleus of the atom is very small but massive. Then secondly, most of the atom is empty space, okay? 3, the negatively charged electrons revolve around the positively charged nucleus. Okay, so we can bring out those conclusions from the successes of this model. Okay, so let's move to the next slide. Now, here we are going to be looking at the limitation of the Rutherford model, and one of them is that the model predicts that light of a continuous range of frequencies will be emitted, whereas experiment shows line spectra instead of continuous spectra. Okay, then 2, the model predicts that atoms are unstable, since in a Rutherford atom, the electrons will quickly spiral into the nucleus due to attractive force between the negatively charged nucleus and the electrons, and the atom would collapse thereby. In contrast, however, we know that atoms are generally stable since the matter around us is stable. Okay, now let's discuss about the Bohr's model, okay, which is the third model we are going to be considering in this topic. So it was clear that Rutherford's model was not sufficient to explain experimental observation and the stability of the atom. This prompted Niels Bohr, a Danish scientist who had studied in Rutherford's laboratory, to propose a model of the hydrogen atom in 1913. Let's move to the next slide to see the postulates, okay? So first, according to Niels Bohr, he said that the electrons moves around the nucleus in certain specific and stable circular orbits, also called energy levels, and that the centripetal force due to this motion counterbalances the electrostatic attraction between the electrons and the nucleus. Okay, so as you can see in the diagram on the screen, you can see that the electron, okay, did not move because of the attraction of the nucleus to the electron, did not push the electron, okay, down into the nucleus. So according to this man, okay, there is a centripetal force between the electrons, okay, and the positively charged nucleus, okay, that counterbalances these two. Okay, then B is said that the energy of the electron can have only discrete values, okay, that the energy of the electron is said to be quantized, okay, it's said to be individualized. That's what that word quantized means. Okay, so Bohr therefore postulates that electrons in an atom cannot lose energy continuously, but must do so in quantum jumps. Now let's move to the next slide. Now, he also postulated that energy, that is light, is emitted only when an electron jumps from one stationary state to another of lower energy. The energy is emitted in the form of a photon of light with energy E and frequency F. So the energy is given as E change, or delta E is equals to HF, which is equals to E2 minus E1. Where H is equals to Planck constant, okay, and Planck's constant is equals to 6.626 times 10 raised to the power minus 34 jouleseconds. Similarly, when an electron jumps from a lower energy level to a higher energy level, it absorbs energy, and this is called excitation. The excitation energy is also given as delta change, that is change in E is equals to HF, and that is equals to E2 minus E1. Okay, so Bohr was able to account for the appearance of line spectrum rather than a continuous spectrum. Let's move to the next slide, please. So this is just the diagram of what Bohr was trying to explain. Okay, so the first diagram here, A, is when photon is emitted when electron moves to a lower energy level. That is, when an electron moves from a higher energy level to a lower energy level, then photon, okay, that is energy in form of light, is emitted. While B is the diagram of when energy is absorbed. That is, when electron moves to a higher energy level from a lower energy level, and this is termed excitation. Okay, so number 3, another postulate of Bohr's model is that the angular momentum of electron was in discrete values. That is, it is quantized. The angular momentum is given by L is equals to ME, that is M under R subscript E, then V subscript N, R subscript N, and this is equals to N bracket open H all over 2 pi, okay, where M subscript E is equals to mass of the electron, V subscript N is equals to velocity of electron in orbit, Y in orbit N, okay, while R subscript N is equals to radius of electron in orbits N. And he said N could take the value of 1, 2, 3, 4, corresponding to the value of the permitted orbits. The integral N is called a quantum number. Okay, so the letter N actually represents a quantum number, and it can take value of 1, 2, 3, 4, etc. Okay, and this is corresponding to the value of the permitted orbits. Now let's move to the next slide. Now on the next slide here, we are going to be looking at the successes of this model. So one of them is that the quantization of angular momentum first proposed by Niels Bohr is a key point in modern atomic theory. 2, it gives a model for why atoms emit light spectra and accurately predicts for hydrogen the wavelength of emitted light. 3, it offers an explanation for absorption spectra. Then 4, it offers an explanation for the stability of atoms, stating that the ground state is the lowest and most stable state for an electron. Then 5, it accurately predicts the ionization energy for hydrogen as 13.6 electron volts. So ionization energy is the energy required to remove the electron completely from the atom. Okay, so that is just the meaning of ionization energy. Now let's look at the limitation of this model. One of them is that it provides no insight into what happens during transition from one orbit to another. Let's move to the next slide to see the remaining ones. 2, the model cannot be extended to atoms with 2 or more electrons. 3, an electron moving in one of Bohr's circular orbits forms a current loop and should produce a magnetic moment, but a hydrogen atom in the ground state has no magnetic moment due to orbital motion. So these are the limitations of his model. Now let's talk about the last model which we'll be considering in this topic, and that is the electron cloud model. So the electron cloud model visualizes the atom as consisting of a tiny nucleus with the electron moving rapidly around the nucleus and spending most of its time in high probability regions. Okay, so the electron is not considered to be orbiting around the nucleus, but it is considered as a wave with a specific energy having only a certain probability of being in a given region in the space outside the nucleus. So the electron is visualized to spread out around the nucleus like a cloud. So the figure below illustrates the distribution of the electron cloud's density. The density of electron cloud is greater in the region nearer to the nucleus and reduce in the region further from the nucleus. Okay, and the reason for that is because of the attractive force, okay, that exists between the nucleus and the electron, right? So let's move to the next slide. So within the spherical boundary is where the probability of finding the electron is high, while the diameter of the nucleus is found to be in the order of times 10 raised to power minus 15 meter, which is consistent with the other model. So this is just the diagram illustrating the electron cloud model. Okay, also showing where the probability of finding an electron is. Okay, so this is the nucleus, the positively charged nucleus, and these are the dense electron clouds. Okay, while these electrons that are further away from the nucleus are the less dense electron cloud. Okay, so let's move to the next slide. So on the next slide here, we are going to be looking at some worked examples. Okay, so example number 1, here we are asked to state 3 conclusions that can be drawn from Rutherford's experiment on the scattering of alpha particles by a thin metaphor in relation to the structure of the atom. So according to Rutherford, he said that the nucleus is positively charged. He said that the electrons moves or revolve around the nucleus, and he said most of the atoms are empty space. He also said that the nucleus is tiny but massive. So those are some of the conclusions, okay, we can draw from Rutherford's experiment on the scattering of alpha particles. Okay, so let's move on to question 2. So J.J. Thomson's model of the atom was abandoned because A, it could not explain the scattering of alpha particles through large angles. B, it did not account for the neutron. C, it did not account for the size of the atom. D, it was known as plum puddle model. And E, the model was not similar to any observable phenomena. So the answer to this question, basically here we are being asked why this JJ atom abandoned its model, right? So the answer to this question is A. Okay, he could not explain the scattering of alpha particle through large angles. I think that is one of the limitation of the Thomson's model. Okay, so let's move to number 3. So number 3, Bohr's model of the atom could not explain the A, composition of the nucleus, B, distribution of charges in an atom, C, penetration of an alpha particle through a metaphor, D, repulsion of an alpha particle by a metaphor, and E, stability of an atom. Okay, so the answer to this question is option A. So the Bohr model of the atom could not explain the composition of the nucleus, but he was able to give explanation from option B to option E. Okay, so the answer to this question is option A. This model, Bohr's model, was not or could not explain the composition of the nucleus. Okay, so this is where we bring the preview of today's video to a close. I believe you enjoyed it, but don't worry, you can watch the complete video by simply clicking on the link in the description below, and that will take you to my school website. There you will have to subscribe to enjoy the complete video. So in the complete video, we discuss about atomic structure and properties. We also discuss about isotopes, and of course we cap it up with some worked examples. Okay, so I believe you enjoyed the preview of the video you just watched. If yes, please do not forget to hit the like button, click on the subscribe button, and lastly tap on the notification bell to get notified whenever we post the next video.